Pleased to host. We're pleased to welcome Dr. Aditya Khosla today from Path AI. He's the CTO of Path AI, and he completed his PhD in machine learning and computer vision at MIT, and MS at Stanford, and BS at Caltech. So he's the recipient of a Facebook fellowship, and his work has been widely covered by various media outlets, including BBC, the New York Times, and the Washington Post. He has published several papers, got a huge amount of citations as well. So we are delighted to welcome him. We would like to know about his work at Path AI and what AI in pathology means and how it can help in precision medicine and so on. So Aditya, the floor is yours.
Cool. Awesome. Thanks so much, Neeraj. Thank you so much, everyone, for being here. And thank you for having me at this seminar. So yeah, I'm happy to get started. So, the title of the talk is AI for Pathology. Just as a disclosure, I'm definitely not, covering the field in its entirety. The talk here is focused very much on the work that we're doing at Path AI rather than the field entirely. There's so much going on in the community, and I just want to make sure it's a fair representation that I'm not covering a lot of the great work that is happening, but it's a little bit more focused on our view of the world at Path AI, as we've been working in this space for a number of years now. With that, the second, I think, important disclosure here is I'm a computer scientist, not a pathologist. So I hope nothing I say is offensive towards pathologists, as well as if there are any questions that might be very specific to the medical domain. I've obviously learned a lot more than I knew 5 years ago, but I may not be equipped to answer all of those questions. But I'll do my best to try. Yeah, so my knowledge is more from the computer science side of things, and as Neeraj mentioned, my PhD was more on the machine learning and computer vision side rather than the pathology side. So my co-founder is a pathologist, so it's been an awesome last 5 years learning from him about the field and working in it. So with that, let me get started. And as Neeraj said, as we talked with Sabine, please feel free to ask questions throughout the presentation. I'm happy to answer any questions. So you can use the chat or feel free to unmute and ask any questions. So firstly, I just wanted to start at what is pathology, because for me as a computer scientist, the first time I met my co-founder, I was like, what is a pathologist? Like, why do you guys exist? And for many of you who might be coming from the field of CS rather than medicine, you might be wondering the same thing. So I figured it's good to just start with some of the basics that might help you understand what is the type of problem that we're actually working on. So basically, pathology is often considered medicine's ground truth. So what happens is a patient gets sick. They might go to a clinic. In the clinic, they might have they might do, say, an X-ray or something. And turns out that there's a lump or there's a tumor somewhere in some part of the body. The next big question that comes up is that tumor cancer or not, right? Or what exactly is going on, right? And so that's where pathology comes in, where the doctor does a biopsy. So essentially, they literally take a needle and poke it into the tumor and take out a small piece of that tumor. That is then reviewed under a microscope by a pathologist to answer the all-important question of, does the patient have cancer or not? Or, if it's not cancer, is it some other disease that the patient needs to be concerned about? And based on this diagnosis, so this is essentially considered the ground truth, right? So the pathologist is that final person making the call of whether or not a patient has cancer. And based on this diagnosis, is the rest of the patient's life is determined, right? Like if it turns out that they don't have cancer, then great, right? Like there may be no treatment, or maybe there's like minimal treatment where they might remove the tumor rather than leaving it in. Or alternatively, if it is cancer, you have to figure out what is the next course of action, right? So as you can see, this is so important in a patient's chart, because it essentially informs all subsequent medical decisions and basically their life after this point. So now you might be wondering, what exactly is it that a pathologist is looking at, right? So let me share with you a few example images of what a pathologist is actually doing, so you can understand how difficult this task truly is. So here's some examples of tissue as it looks when it's viewed under a microscope. So when you take out this, like the piece of tissue from a tumor, it usually essentially is transparent, right? So you won't actually have any colors on it. So what you do is you process the tissue by dunking it in certain chemicals and removing the moisture, embedding it in a wax block, so on. Like there's a few different steps, and there's a fairly standard pipeline of processing the tissue that results in the tissue looking a few different ways. So in this particular case, you can see that the tissue has been colored this pink and blue sort of colors, and that's that stain is called H&E, or hematoxylin and eosin, and those colors essentially allow a human to better interpret these images and say, hey, can I find cancer cells or not, right? And so the other thing you'll notice is that these images all look quite different. Like these are all normal tissue regions, but because they come from different parts of the body, it looks different, right? So essentially, you guys might remember when you learned in biology, right? Like your tissue differentiates and forms these different organs. And when you actually look at these organs under a microscope, they don't just all look the same, right? And different organs will have different structures, different shapes, and so on. That pathologists often can even tell which organ a particular tissue specimen is coming from. And pathologists need to take into account all of this information to make a diagnosis as to whether or not a patient has cancer, right? And that, you can see, is a pretty hard thing to do. This is, example of images where, these are examples of images that contain cancer. So you can see that there's these, enlarged cells in this particular tissue, and in this, and you can see these are quite tightly packed. In this one, there may be a little bit more spread out. These ones, again, these are the cancer cells right here, and these are all more spread out. And a pathologist has to zoom in, has to look at small regions like this to figure out whether or not a patient has cancer, right? And you can see that there's so much variability in how just the cancer looks across the board, which a pathologist has to, understand and be able to interpret effectively. The other thing you notice is that, each of these things have different colors, and those, color variations are another consequence of how the tissue is processed, right? So if the tissue is prepared in one particular location versus a different location, a lab, essentially, that can cause the tissue to look different. And that's another type of variation that, a human can be quite comfortable at dealing with, while, it can be challenging for machines to interpret. Here's actually other stains that look even more different. So instead of using, the standard chemicals called hematoxylin and eosin, you can use, these things called immunohistochemistry markers that turn, cells brown, for example, based on whether they're expressing a certain kind of protein, or, just identifying basically different biomarkers. And so a pathologist is not just looking at those, previous images that I'd shared, but also looking at images like these to help figure out, and oftentimes help figure out what is the best course of treatment for a particular patient. So as you can see, a pathologist's job is hard. The other big thing here is what I'm showing you is actually such a small part of the full tissue specimen that a pathologist looks at. It's kind of crazy how much, tissue a pathologist is processing. And a single pathologist typically looks at about, so right here, you might be seeing about, few hundred cells in each of these snapshots. A typical biopsy might have on the order of 10,000 to 100,000 cells. And a pathologist normally looks at on the order of 300 slides every single day, right? And their job is to not miss a single cell as being cancer. And that's a hard job, right? Imagine yourself looking at, this, whatever, about 30 million cells every day, and you can't miss a single one as being cancer. So as you can imagine, what happens as a result of it. So here's a few more, different types of stains and variations that a pathologist has to interpret. But as you can imagine, what happens as a result of this is that, discordance is can be common amongst pathologists, which means that, you can take the same tissue specimen to different pathologists and end up with different outputs. So think about that for a moment, right? Like that is kind of crazy, right? So firstly, we say pathology is considered medicine's ground truth. Now you're telling me that, if I talk to different people, I may or may not have cancer, right? Like that is, whether or not you have cancer should not be a function of the doctor that you're seeing, right? Like you either have it or you don't have it. And what they're showing here is actually a relatively simple experiment where they took the same sample. So each of these columns here corresponds to a single sample. So, you can see 106 was one of the patient samples and 116 was another patient sample. They showed each of these samples to about 30 pathologists and asked them to make a diagnosis independently, right? Because obviously, you don't know which pathologist you might end up with. I don't know who I might end up with. But you'd hope that, that output would be very consistent. Unfortunately, what they found is that the overall concordance on these breast biopsies only had a rate of about 75%. And that's pretty scary, right? So essentially, if you look at a case like, some of these ones in the middle here, basically what you're seeing is the different colors represent different diagnoses. So essentially, there's a third of, so if you look at this case, right, just for simplicity, there's about a third of pathologists saying it's benign, a third saying it looks atypical, and the other third saying it's cancer, essentially, like ductal carcinoma in situ, which is cancer, the early stages of cancer, essentially. And so the course of treatment that a person would follow based on each of these different diagnoses would be quite different. And we need to be able to fix that, right? Like we essentially want to have consistent diagnosis happening for every single person, right? And so the question is, how can we do that going forward? So as with most things these days, the answer is obviously AI. And so the question that often comes up is why now, and what can AI do essentially, right? In this particular case. So the first thing that I think might be worthwhile answering is why now, right? So this was actually a really interesting paper that I had published with some of my collaborators back in 2011, where we had taken the state-of-the-art model for identifying cars and tried to study it in many different ways. And the model was so awesome, it could basically find a car anywhere. Back in the day, the sentiment in the field was just so different than what it is today. For those of you who have been through it, back in the day, we used to say, oh my God, this is the state of the art. The rate at which it's advancing, it was like, depressing optimism, maybe I should call it, where, the depressing part was like, yeah, this is never going to work. The optimism was, hey, at least we're going to have a job for the rest of our lives. Because, we're going to keep trying to make this work. That was the case in 2011. And now, come to 2021, and we're talking about all sorts of things that AI can do, right? Like talking about, killer robots and AI getting consciousness and destroying the world and all of that kind of stuff. I think the truth is somewhere in between where we were and where we are now. I think AI has come a long way in recognizing patterns. And if you looked at all the images, we're very far from consciousness. At least that's my belief. Of course, maybe if some of you guys are working on things that might get us there, but I think we're pretty far from it, but AI is able to recognize patterns consistently. And if you look at the images that I'd shown around pathology, it should be pretty clear that it is sort of a pattern recognition task. Like if you look at certain types of cancer cells, you guys could probably start recognizing more cancer cells, and we could probably teach deep nets how to do the same thing. And so one obvious solution here is, what if we applied this to pathology? Another thing that shows promise, and I'm sure you guys have probably seen this before, This is the ImageNet performance over time. So, ImageNet challenge, I think which has now ended. This was a huge challenge back in the day, where, the goal was to recognize across 1,000 different categories, the different objects that might exist in each of the images. And, if you see in 2010 and 2011, the field was progressing forward. So, less is better because this is the error rate. The field had been progressing forward slowly, and this probably was one of the good years. So nobody was expecting that huge improvements would happen. But back in 2012 was when deep learning was first introduced, and you can see how the error rate suddenly fell. And the awesome thing is that over the last few years, deep learning has improved considerably. Where now for this particular task and for one particular human, the machine, like deep nets, can actually perform better at recognizing those 1,000 objects than a human can. And this was obviously a smart human, as many of you may know. And so this means that the technology has advanced enough that we can actually utilize it for this type of a problem in pathology. So yeah, and this idea of deep learning has obviously been applied in many different industries, and pathology is just one of the use cases, but it is clearly driving so many advances across the industry. All right, so now let's get back to the question of what can AI do for pathology, right? So basically there's a few things that AI can do for pathology. Firstly, it's exhaustive, right? So as I explained to you, we were looking at a very small snippet, and maybe you can look at that exhaustively, but as I've said, a pathologist is looking at a whole lot of data every single day, right? And that can be tiring, right? And you might have, like if you're distracted even for a moment, you might miss something that is super important, right? And obviously, all of us as humans, and pathologists in particular, are trying to do the best they can, right? They understand how important their role is, but as a human, it's hard to do that same thing over and over, in the most accurate way every single time. Whereas with a deep net, you can look at every single pixel every single time, and that's awesome. The other big thing is that the model is quantitative, right? So even though humans can take a look and try to guess, like, okay, there were 20% of cells that were brown, or 5% of cells that were brown. What many studies have shown is that humans can be quite like discordant in some of those situations, because you're trying to look at such a big piece of tissue and trying to figure out how many of the cells were positive for a particular biomarker, right? And that can be very, very challenging. It's almost like showing you a jar of marbles and saying how many marbles are in there, right? And you're going to get quite a variety of answers. And of course, there's ways to try to guess that more accurately, but it's a hard problem, right? Whereas if you could actually take out each marble and count it, you'd get the right answer, right? Which is what you can do with these type of models. The other big thing, of course, is that it is efficient, right? So the efficiency piece is actually really important in this field, because one of the interesting things that is happening in pathology is that the number of pathologists has actually been reducing over time, right? So, and the other thing is that, while the US actually has a decent number of pathologists, if you look around the world, the number of pathologists is actually quite limited. I think I'm forgetting the exact numbers, but they're quite striking where, if you look at how many pathologists exist per human in the US versus if you look at it, per person in, say, India or China, it's literally a difference of about 20x. And so you can see how much more overloaded and overworked pathologists outside the US are going to be. This type of efficiency is extremely valuable when you're trying to apply this technology, more broadly. So, sorry, I see the chat.
Yeah. So yeah. I was about to read that question from Kiran, that if we are using AI instead of human being tired, would the new constraints be processing speed?
AI instead of human being
tired. So would processing speed be the new constraint if we
Yeah, I think that's a
maybe
great question. I personally don't think processing speed is the constraint. I think the constraint is more like it's probably how can we build models that can better mimic humans, right? I think humans are like, and this is the challenge with the entire like field of AI, right? Everyone's working on how can we build models that can generalize better. And I think in pathology, you have the same set of challenges, right? So the few things that humans are really good at is, they can learn really well from from very few examples, right? How can we teach machines to do the same, where you may have diagnoses that are super important, but don't occur that frequently. So you don't have that much training data, right? The other thing that I showed you is there's so much variation in how tissue can look under a microscope, right? And to build models that can be can overcome that type of variation when different labs or different people are preparing the same piece of tissue and still give consistent output. I think that's probably a much bigger challenge than processing speed. But I think it's a great question. So yeah, but I think with people doing web scale stuff, the number of biopsies is actually much fewer compared to, say, the number of selfies uploaded on the internet. And so while people are able to process that, like this stuff is relatively low overall. It's not easy to do it, but it's definitely not as big of a scale as some of them.
Aditya, there is another question.
Sure.
What is the global coverage of PathAI and what has the growth rate looked like? What is the main factor driving its success? I don't know if you would like to take it now or towards the end. So I leave it up to you.
Sure. I'm happy to just, answer it to some extent. So yeah, so right now, our first set of customers have been more on the pharmaceutical side. And, I'll talk a little bit more about the type of applications and use cases there, where, this can be used. So I'll pause for that. And I think the growth rate has been, I guess some of it I can't discuss publicly, but it's been good. We've been working with the majority of the top 20 pharmaceutical companies, and more recently bought a lab which processes tissue samples, giving us access to a lot of data, as well as starting to work with more and more patient samples over time, and applying our techniques to those, real patient samples that are flowing through the lab. So, yeah, I think the main factors driving our success, I think it's, first off, right, like it's important to acknowledge the technology actually works. I think we're doing a really good job, but there's a lot of companies doing great from a technology perspective. We like to think we're ahead, but at the same time, tech transfers pretty quickly, and people all have solid tech. So I think for us, I would say our main factors, and I don't want to I think it's important to realize that the tech is essential to your success, but that can't be your only driver for success, right? And I think for us, we've been really fortunate to have phenomenal tech, and I think leading the industry. But at the same time, I think a lot of the other factors, such as our approach to market, the way we develop the tech, in terms of having a more very narrow approach to one disease area versus building a platform that works across multiple disease areas, having a more breadth of offerings that actually align very well with what our customers are looking for. I would say a lot of those things are probably, hugely contributing factors that have led to our success thus far. And obviously, the journey is just getting started. Yeah, but we've been fortunate thus far. Cool. So, I think this last point might actually help also explain what type of problems we're often working with, pharmaceutical companies on. So the other big thing that comes with being super quantitative and exhaustive is that you can now start to explore new types of features, as well as new types of relationships between those features and how patients are responding to treatment, right? So essentially, there may be features that a human might have a really difficult time quantifying by eye that can be learned in a much, like that can be derived based on what we are, what we output from the models. And those features can then be correlated with, say, like to give you an example, if, suppose a patient took a particular treatment and they lived for a particular amount of time, can you actually build features that can predict how long somebody would live if they were to take a particular treatment, right? So that can allow you to match patients to the right treatments. And that can be extremely beneficial, both for patients and of course, for companies developing these drugs that can better target the right subset of patients. So those type of relationships can be, humans have been trying to do it by eye for a long time and they've been great at it. It's amazing how much progress we've made, but imagine being able to generate, almost infinite features and correlating that with how patients are doing. There's a high likelihood that we can do, much better than just trying to do this by eye, because it's also both more accurate features and a much larger set of features. So I'll talk a little bit more about that as we get further into the talk. Cool. So, just one thing good to highlight, what AI can't do for pathology is replace pathologists, right? Like, I think the task that they're doing is extremely challenging, and, there's a lot of nuance in a number of things that they do. And I think the way we approach it is try to augment pathologists along the way, in different tasks that they're trying to perform. There may be certain things that can be done to make, their lives easier, where a pathologist is, just overlooking the AI with less and less time needed. But I think at the end, the pathologist understands a lot more than I think AI can do anytime soon. So, yeah. So I'll give you a specific example, and so if you have questions, again, please feel free to ask. So I'll give you a specific example of something that we worked on a few years ago. This was in breast cancer metastasis, where so essentially, what is breast cancer metastasis? So after a primary node is discovered, in the breast, or like a mass is discovered, which is cancer, you need to figure out how far the cancer has spread. And so, you usually biopsy lymph nodes to figure out, okay, is there cancer there or not? And, pathologists check for these to see if cancer is spreading, and allows you to figure out the stage of cancer. So, this thing is supposed to be a relatively straightforward task. But a retrospective study found that this actually has a non-zero failure rate. So there's folks who are interested in exploring this and seeing, can you build models that can reduce that failure rate, like by training and applying to certain data sets. So this was very much this type of, this was almost like an ImageNet challenge setting, where they had provided a data set where you could download, the slides with some training annotations, and you upload your results back to their server, and they would evaluate on obviously a held out test set. They would evaluate how your model's doing and report the performance out. So it's called the Chameleon Challenge.
Question.
Go for it.
So you're talking about the previous slide. You're trying to predict which ones will later have metastasis, or which ones are currently metastasized.
This is currently metastasized. So essentially, the goal here is to look at actually the lymph node biopsies and figure out if they contain cancer cells or not.
Okay, thank you.
Sure. But I think that would be a cool, cool task as well, if you could figure out which ones will later metastasize. But I think getting the data for that might be a little bit challenging. But I think that would be a cool thing to try. Cool. So the next thing, so basically, they shared this data. This was called the Chameleon Challenge, where they had, H&E stain data with, about 270 slides and 129 tests, like 270 training slides, 129 test slides. They'd annotated all these regions, as you can see, this was normal, this was cancer, and they'd done this across the entire slide. So the goal there was to figure out, where all the cancer regions are. And what we did was, we applied a relatively, there was a number of tricks and such in there, which, I'm happy to talk about, which we've published on. But essentially the idea here was, let's train deep nets to figure out where the cancer regions are and where the normal regions are. So one of the things that we did was, all right, let me see if there's a question. How have you solved the challenge of getting access to training, how have you solved the challenge of getting access to training data, deploying models, and making them available to your customers on demand? I think that's a great question. Let me talk about, the process of training the models, and then I'll be happy to talk about, getting access to data and things like that. So basically, the way we train the models is that we want to annotate, we use the annotations provided by the pathologists from this competition. So what they have labeled is, okay, here's the tumor region, here's the normal region. And so you'll have these, what we do is we extract little patches from this. You train a deep net, pick your favorite architecture. There's a new one every day. You train it, and you ask the thing you predict in this case could just be as simple as what is the probability of tumor, right? So 1 for these patches and 0 for these ones. And then what you do is you take a test slide and you again break it up into these little overlapping patches. You apply the your model that you have previously trained, and that results in a tumor probability map such as this one, where the red regions represent tumor while the blue regions represent normal, at least according to what the model predicts, right? And so the question that had been brought up in the chat was, how do you get access to training data, right? And all of this is a great question, right? So this was something that was just given to us, right? When we had just started testing out this approach. So we get access to training data in multiple different ways. So firstly, we have partnerships with our pharmaceutical pharmaceutical companies where they share data with us. But the thing that's a little bit challenging is that that data is not annotated, right? So unlike this competition, that data does not contain these nice regions that say here's cancer, here's not cancer. In fact, that data can be quite noisy as well as quite and completely unannotated. Sometimes annotations are in fact wrong, things like that, right? So what we do is we actually have internally built up a mechanical Turk of pathologists. So we have over 400 pathologists on our network that would annotate this data that can then be used to identify each of these different regions. So apart from our pharmaceutical partners, as I said recently, we also purchased, acquired a lab. That lab processes around 1 million samples or so a year. And we can get access to that data for research purposes, of course, under the right IRB approval and things like that. Start using it from there. And I think there might be another part to that question. So deploying models, the way, I guess some of this depends on, your business model, whether you're deploying, whether the customers are deploying or you're deploying. So in our case, we deploy the models and make the results available to customers. So essentially to deploy models, again, there's many things you can go into in terms of computation and all that stuff. So we have our own, data center where we deploy all of these models as well as train them for a large variety of use cases. So I hope that answers your question. And yeah, if you have something more specific around the deployment of models, I'm more than happy to chat about that. Cool. So now the question is, how did that model perform? So what we found is that, this deep learning model outperforms human pathologists in the diagnosis of metastatic cancer. So essentially what they did was that this was the competition organizers. So they told the pathologists in the competition that, hey, look at all of this, all of these slides, please do the best you can. And, try to take as much time as you want. Try to figure out, try to find all the different regions of metastatic cancer. In that case, the pathologist's error rate was at about 3.5%. This was again on the test set that was, like where the labels were not visible to our system. In the other case where pathologists were told to act as though they were doing it in clinical practice, where this is a case where they have to read these 300 slides a day and have to like work quickly to get through all of the slides. That error rate actually went up to about 13 to 26%. And the other thing that is, in certain cases can be concerning is it's actually on the smaller cancer where the error rate was much, much higher, as you might expect, right? As I talked about, they have a hard task to do looking at all of these slides. So this micrometastasis actually refers to small tumors. In that case, the error rate went up from 23 to 42%, while our deep learning model performed consistently across the small or large cancer regions and had an accuracy or had an error rate of about 0.65%, right? And the hope is that by combining our system with a pathologist, we can get that error rate down to 0, right? So that every patient gets the right diagnosis every single time.
Can I ask a question again?
Go for it.
Pathologists are like 3 or 4%. If they try really hard, they still make 2% errors. How did you define truth? Is that a consensus of pathologists? And is that really the best way to do it?
That's a great question. I guess that's the best way we know as of now. But I think, so there was 2 ways that this particular competition did. And I think it does not apply for every single indication, but in this particular case, it was a consensus of pathologists, but there's actually for, some of these, like they also use this thing, like a special stain called like cytokeratin, which they use, right, like for determining ground truth. So this was on, the model was trained and tested on H&E, but some of the ground truth came from like a serial section of cytokeratin.
Good. Well, I'm going to come back to that later on, but thank you. Great answer.
Sure. Cool. So the hope, so essentially this this could be what the future could potentially look like, where a pathologist typically these days is faced with empty slide and have to figure out where the cancer cells and such are. Instead, what they could have is a heat map such as this one, which highlights in red, like, all right, here's the regions that the system thinks are cancer. They could potentially look at some of these regions to make a quick diagnosis. So if you look at it right here, like these are actually cancer cells, which could have been fairly easy for a human to miss, given that they're in such a large mass of other cells, while a machine will pick it up quite consistently. So in the future, one possible future here is that, currently a pathologist, when faced with this image, would look at different regions at random, well, not completely at random, but, look at different regions, somewhat at random, somewhat systematically. And these are showing sort of those field of views of like, they might zoom in certain regions and not zoom in as far in others. And so they're trying to look at it, sporadically, and they're faced with this empty report, where it takes time to fill in this report, as well as the accuracy might be low as shown in the previous set of results, especially in the clinical practice, and reproducibility is low as well, where where people in the community again have done studies to see would the same pathologist with the same input data, so the same slide, produce the same diagnosis every single time. And they found that even that can be discordant to a reasonable extent. So instead, with PathAI, the hope is that you have this heat map, you have these regions identified, pathologists can do a quick review. You have a report that's pre-filled based on a lot of this information. What they would have to do is either confirm or deny that diagnosis. And hopefully what this can do is reduce the time significantly, as well as have a much higher level of accuracy as we had seen with some of the previous results. And given that the AI is just deterministic and consistent based on input regions, you would have high level of reproducibility compared to like a human looking at this alone. So Yeah, so that's, oops, sorry. Huh, I don't know why this is doing this again. There we go. All right. So with that, I'll switch, from cancer to this non-alcoholic fatty liver disease. So this is another use case where we found, the use of AI to be particularly helpful and impactful for patients. So for those of you who are not familiar, NAFLD is like non-alcoholic fatty liver disease. So this is essentially a disease that affects people who don't, this is not something where alcohol has caused, cirrhosis, but or NASH in particular, but rather just people who don't consume alcohol still end up in this situation. So essentially, and this disease can often lead to negative outcomes for patients. And it is estimated that about 30 to 40% of US adults have NAFLD. It's claimed to be, I think, underdiagnosed at the moment. And of those, 20% have NASH, which is, the stage just before cirrhosis. And, once you get to cirrhosis, it can be pretty difficult to reverse that outcome. Yeah, so essentially people have been trying to catch it in the NASH stage and seeing, can we bring it back to, either like to one of the earlier stages. So this has been actually a pretty big area of focus for drug development. As you know, it can have a huge impact on a large fraction, of the population. As of now, there has been no FDA-approved medications, and many trials have actually failed their endpoints. And one of the things that we found in the industry, and I think this has been independently discovered as well, is that the suboptimal reliability of this biopsy evaluation has probably led to some of these failures. So essentially, when you read, you're trying to see if you're bringing the liver from a later stage of fibrosis to an earlier stage, and that can be pretty challenging for humans to figure out. Plus the other, apart from that in and of itself being challenging, it's not as precise when you look at the data, right? Because typically what a human is doing, and for those of you who are familiar with how the staging works, you would look at the max, if there's any part of that biopsy that is at the max, at the highest stage, that would be the stage. Even if it's just corresponding to 5% of the tissue, that is the stage that is assigned to that biopsy. Whereas, it might, whereas if a patient has that same stage at, 50% of the biopsy versus 5, that's not seen or treated differently, right? And reversing those, that final stage can actually be quite challenging, potentially for, given how much time in the trial and such you have. But you can imagine if, the proportion of earlier stages of fibrosis increases after you give someone a particular treatment, but not that very, not the, the final stage is not completely gone, it may not show drug effect as accurately, if that is the endpoint that you're going after. So essentially what we did was, hey, why don't we try to predict this, and both try to do a better, try to see if we can be more consistent at predicting, fibrosis and some of these other NASH markers, as well as, can we quantify it more accurately, right? So instead of saying, okay, it's just fibrosis stage 6, can we say, okay, there's 10% of stage 1, 20% stage 2, blah, 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 right? And then quantify how much on average has the amount of area with lower stage fibrosis increased after treatment. So essentially what we did, we built, similar type of models as I had mentioned before. So what we had was, we had pathologists annotate each of these different types of regions. So you can see, this is maybe an inflammation annotation. This is a ballooning annotation, steatosis, and so on. This was done on the H&E. You train your favorite deep net again to figure out, to learn to predict these different regions. So I think this model, if I'm not wrong, was trained on somewhere on the order of 5,000 to 10,000 slides. And a lot more labels than that were produced by expert pathologists. And you can apply that model back and predict for every single pixel what kind of, if there's steatosis, ballooning, inflammation that occurs at that particular region. And you can see here the heat map is colored in different ways to indicate the different regions that are being predicted. And similarly, you can ask pathologists to provide labels for the NASH fibrosis score at like the NASH stage at the slide level, and again use a CNN model to make that prediction. And what we're able to do is also identify what regions are like contributing to the different scores essentially. So using that, you can kind of make this heat map of like, this is F0, this is F1, F2, F3, F4, and so on. So the first thing that we want to do is, see, is our model actually predicting anything meaningful, right? Like, does it correlate at all with a consensus of pathologists, right? So instead of any single pathologist reviewing this, we wanted to see, I think we got, if I'm not wrong, 3 to 5 pathologists per slide to provide the fibrosis score. Then we took the consensus median and correlated that with what our model was predicting. So you can see it actually does a reasonably good job with the R of 0.835, and the p-value of the correlation being significant is obviously super, super small. Yeah, so essentially we saw that predicted it accurately. The other thing is that we were able to also start quantifying the amount of fibrosis at different stages for each of the patients, right? So if you look at a central pathologist for, say, this particular slide, they would have just assigned a score of F6. Whereas if you look at the whole, if you look at the slide in its entirety, there's actually much more nuance than just, this patient being F6. There's, the fraction of the tissue that is F6 is only, say, 22%, while there is, 47% that's F5 and so on, right? So one of the very interesting things that we found is that, this fibrosis score that we had predicted was associated with time to first clinical event. I think this was to like cirrhosis, if I'm not wrong. I'm forgetting the exact, the specifics, but this work is published and, you guys can check it out. But essentially we were able to make more meaningful predictions using our tool, as well as more accurately quantify, the stages of the disease and how much the disease might have regressed based on treatment. So we're currently in talks with, a number of pharmaceutical companies and the FDA to like bring this to patients. We've already started using this, in a few different places for analysis, but it's important that we start bringing some of these findings to impact like patient outcomes.
Quick question.
Go for it.
Are these actionable differences? If you have the more precise definition, can you now say, now he gets this drug rather than that drug? Has it gotten to the point where you can do that at this point, or are we still?
I think my guess is that it would be, but I think it just, so one of the things is for like, my guess, yes, it would probably be actionable in that way. But I think for most of the people who are working on NASH right now, I think they don't want to, like, I don't think biopsy is the regular course of like action, right? Like I think everyone wants to use non-invasive testing to figure out if a patient has NASH. And so I think that's where they want to, that's probably the markers they want to use to identify like, which is the best course of treatment. But I think the FDA still thinks of the, biopsy as the endpoint that is used to determine, the stage of the disease. And so by not being able to do that as accurately, like we believe there may actually be some decent drugs that have failed trials because I think the FDA has felt, somewhat uncomfortable with how this staging has been done. And so we want to, help improve that and allow some of those drugs to come to market.
Cool. Thank you.
Sure.
And the results reported here just use fibrosis score for Khosla model.
What do you mean? Like, yes.
So when you predict the time to first clinical event, it just uses this fibrosis score, ML-generated fibrosis score as it. No other way.
I believe so. I think you might, like, I'll have to look, like, I'm sure we try, like, because, you know, it's routine for us to try either one feature or multiple features. Like, I don't, like, you know, this paper is a couple of years ago, so I'm sorry I forget the specific, but it could have been that, you know, this fibrosis score is sort of either a weighted combination of this histogram, rather than just this, you know, F6 versus F5. So that's why it's called the ML fibrosis score. So it was a new score that we defined based on, you know, the distribution of fibrosis that we saw across the tissue.
Because I was thinking if there are other confounding factors, and how would that help in this time to first?
Yeah. So we usually, I mean, it's quite common for us to try the multi-variable models, but I think from you know, customer and like from, you know, our customers who are biopharma, as well as from you know, biology perspective, it is much more I think satisfying if you're able to find, you know, identifiable features that you can do this prediction, like things that are simpler essentially, rather than, you know, models that people are unable to interpret as to what caused, you know, like, yeah, because it's just, when you have a complex set of features, you might do a better job predicting, but I think unless you have a data set that's large enough, you don't know if, you know, there are just some weird confounding variables that are causing that type of prediction that cannot be explained by what you know, by people's understanding of biology. And I think what was interesting about this is that it, like, the two things correspond well. And that's sort of the best, I think, way forward, where you can say, okay, based on, you know, what we know about biology, and based on what we're seeing from here, those two things make sense. And they align with each other. Yeah. Oops, sorry. Cool. Yeah. So I mean, this was, I think, just an abstraction, you know, of like, that's, so what that, like, just to give you like a sense, like this, you know, what this is doing is, this is being like, this is the histologic endpoint, right? Like, this is more looking at, can you evaluate how a patient's disease is either progressing or regressing based on AI. The next thing that you can do is actually, like, you know, like, I think Russ maybe was saying is, can you actually match patients to the right treatments using this type of technology? And that's definitely something that we're working on as well. Where, you know, the problem is, you can imagine it's fairly straightforward, where, you know, you might have patients that have received a particular treatment. What you find is that, say, some subset of patients respond well to that treatment while others don't. And, you know, the task here is to figure out, can you use the information that you had from, you know, before the treatment was given, to find this sort of like decision boundary of who are the patients that are likely to respond to treatment and who are the patients who are unlikely to respond to treatment, right? And classifying this is valuable both ways, right? Like, because for patients who are not going to respond to particular treatment, it's good to know, and hopefully they, you know, they, like, sometimes these treatments can be like toxic or have adverse effects, and it's good to not take it. And obviously for the patients who qualify for the treatments, it's awesome, because, you know, they have a higher probability of being alive, right? And so on both sides, I think it's actually quite valuable. And if you can do this more accurately, this can be extremely powerful, right? And as you know, whoever's in the medical field or, you know, knows about this space knows, treatments are heading more and more in this direction, right? Like, where it's not just like, you know, you have a like headache, just, you know, take this one drug and it works for everyone. But you know, you look at the subtype of disease, you look at you know, what are the causes of the disease, and use that to help figure out the best treatment plan for each patient. And if we can do that more accurately, that would be awesome. So the way to do that, I mean, is, you know, I don't have some of the real data here, because I figured we'd run out of time as I had expected, but the idea here is fairly straightforward. You know, the goal would be to, you know, identify features that can be quite hard for a human to potentially identify, by eye, such as say the proportion of lymphocytes that are within 80 microns of a IHC positive lymphocyte, right? Like that could actually be a feature that reveals why, could predict outcome for a patient. But to quantify these things by eye can be extremely, extremely difficult, right? And so what we can do, because we can build these, awesome heat maps that can identify literally the identity of every single cell, we can start producing fairly complex features and putting them together in these, multivariate models and saying, can you now predict the outcome for a particular patient? And, one of the questions I think that had also come up was where to get the training data for this, right? Because that's hard too. And the answer is, we usually work with our pharmaceutical partners who have collected a lot of this data in their clinical trials, and work with them to, make these make models that can do these type of predictions. And the other interesting bit is that, they are also starting to combine this data with other modalities of data, such as NGS, and, other biomarkers to make better and better predictions than you can from any of these modalities alone. So yeah, with that, I'll pause here. I think what maybe the key takeaway is, AI-powered pathology is applicable across all image-based tasks, and we're working across many indications, at least at PathAI. As AI and digital pathology are incorporated into clinical workflow, we hope that they'll offer significant operational efficiency and quality advantages. And we believe that AI will drive improvements in both the accuracy and predictiveness of pathology, leading to just patients matching with the right treatments much more frequently. So I'll stop here, and I'm happy to take any questions. I know we're like a few seconds over time.
Thanks, Aditya. That was a great presentation. So anyone has questions, please feel free to unmute yourself and ask Aditya directly. We'll have a couple of minutes.
I have a question. I was just wondering if you think that adding the demographic variables for the patient biopsies, does that have any really impact in the models if you have genomic data as well as the pathology images?
My guess is, it's honestly hard to know. I think it probably varies based on what task you're working on. And I think at times it could be valuable sometimes to add some of that information. Not, maybe not just demographics, but other metadata such as like smoking status and things like that, so that, the models don't pick up on, like, maybe it can help you create models that don't just pick up on things that are like less relevant, right? And these variables might explain a lot of the signal. And I think you should use that instead of building even more complex models that don't actually add value. So having some of those variables and seeing if they themselves are actually predictive of certain types of outcomes is I think, critically important. And at times they might augment what the images can do. Yeah.
Any other questions? Because now Aditya will have one-on-one meetings, so I think we should not squeeze into someone else's time where
Sure.
Aditya is meeting. I think Michael right after this. So let us thank Aditya and feel free to reach out to him if you have any other questions. So thanks, Aditya, for coming in today.
Thank you very much.
Giving a great
Thank
presentation.
you.
Yeah, thank you guys for being here. It was great.